For this paper presentation session, Sri Gopinath, scientist E, CDAC Bangalore, will be the session chair. I request sir to please come over the dais. I request Sri B. Ravi Reddy to felicitate scientist E, CDAC Bangalore, to felicitate our session chair.
Yeah, good morning all. A warm welcome. Fine. So this is the third paper session of this conference, first for today. And we have two papers to be presented in this session. And the first paper to be authored is authored by Mr. Akash Angom. Title of the paper: Design and Implementation of a Post-Quantum Double Ratchet using ML-KEM. Okay, can we have the presenter, please? Yes.
Good morning to all. Myself, Akash Angom. I am an MTech student from NIT Agartala. So I am presenting my paper titled Design and Implementation of a Post-Quantum Double Ratchet using ML-KEM. So this is a part of my MTech project where we do a preliminary study on the migration of end-to-end encryption in secure messaging. This is my table of contents. Coming to the introduction, we have the Signal protocol. So it's a peer-reviewed open source end-to-end encryption protocol for secure messaging. So it is used in modern web applications such as WhatsApp and Signal. Now coming to the double ratchet. So it's an algorithm which guarantees that every message is encrypted under unique individual keys. And so traditionally, it is dependent on the Diffie-Hellman key exchange. For example, the X25519. And designing and substituting with a post-quantum secure primitive is crucial in the post-quantum era. And for this niche drafted standard for the key encapsulation mechanism, the ML-KEM is a potential substitute. Coming with the motivation, so the Apple's iMessage chat application uses a PQ3 protocol, which claims to use a hybrid post-quantum rekeying scheme, but the details are not published to the public. And next, the Signal app is developing its own post-quantum upgrade, but it is not yet released. Now, to address this gap, we propose ML-KEM as a replacement for legacy Diffie-Hellman in double ratchet. Now, direct substitution is non-trivial since KEM differs fundamentally with Diffie-Hellman. Coming with the background, our main security objectives of this double ratchet will be to achieve the confidentiality, forward secrecy, message authentication, integrity, protection, post-compromise recovery or break-in recovery, asynchronous messaging, replay attack resistance. Now, the ML-KEM is a niche drafted standard for key encapsulation mechanism that is based on lattice-based crypto with the underlying module learning with errors problem. And ASGCM, it's an authenticated encryption mechanism which use Galileo message authentication and counter mode. Coming with the key derivation function. So a key derivation function takes an input like initial source of keying material and it produces further keys. Coming with the classical double ratchet of Signal, it is based on the Diffie-Hellman exchange where there is two parts in it. like the Diffie-Hellman ratchet and the symmetric key ratchet. So Diffie-Hellman ratchet, mainly it is used to generate a phrase key for every message, and the symmetric key is used to produce message keys. And here the root key, it is generally achieved using the preceding key establishment protocols such as the PQXDH. Now in our design approach, we are integrating the ML-KEM into the protocol, where we try to achieve unique message encryption for and it has two phases. The first phase is handling the initial chain and to obtain the public keys, that is the encapsulation key of both the parties, and to handle the initial ciphertext, which is nothing but the encapsulated key. And in this phase two, we have ciphertext only exchange. So unlike the Diffie-Hellman approach, where there is a requirement to produce a phrase key pairs for every ratchet. So in the case of ML-KEM, we do not require because of the probabilistic nature of the ML-KEM. For implementing, we are implementing in as a proof of concept only. So, and it is written in Python, and the source code is also uploaded in the GitHub. Further, we require the use of a buffer server so as to facilitate the asynchronous communication. In our results and analysis, we have computed the correctness of the protocol based on the receiving chain of one party is equivalent or equal to the sending chain of the another party and the way around. And the security preservation is intuitive here. And it provides the security objective that we have mentioned in our introduction. And next, we discuss the network load. So obviously, due to the increase in key size and ciphertext sizes, so the network load will be definitely increased. And as mentioned before, we do not require to generate key pairs for every post-quantum ratchet. And it is feasible because of the probabilistic nature of the encapsulation, where the seed of the randomness seed is like it's random in nature. Like for every call, it will give a different output. In our conclusion, we give the post-quantum secure variant of the signals double ratchet by replacing the standard Diffie-Hellman-based exchange. And a proof of concept implementation which shows the feasibility of achieving a fully post-quantum double ratchet with real-world usability, and whose source code can be found in my GitHub page. And current and further investigations can examine more refinement, strict mathematical proof of security, and uses fields toward strengthening. And also, I want to mention that my implementation is like from the scratch, like without relying on the external libraries such as OpenSSL, because during my time of the study, OpenSSL has not introduced the ML-KEM as a part of it. So as a result, we haven't performed the performance comparison with other schemes because they haven't really released yet. So these are the differences. Thank you.
Any questions from the audience? Okay. Okay, right. I just have one question. If the key is compromised, how does double ratchet help that to further exchange a new key and
progress with that.
So if key that is encapsulation, the decapsulation key of a particular encapsulation key has been compromised, then there is a updation mechanism where we require the encapsulation key to be updated on a regular basis, like after some certain period of interval, like that is set by the policy which is making that particular application.
Okay, so key revision is the way to adopt that. Is it so? Key revision is the way to revise the key or change the key,
Replacing the
replacing the key. Okay, okay, fine. Thank you. Thank you very much.